Good morning, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. In this session, I would like to explain on important questions which are related to fouling factor and overall heat transfer coefficient also. So these are the questions. What is overall heat transfer coefficient? Explain of fouling factor on heat exchangers. We will address these questions. First of all, we will see what is the overall heat transfer coefficient. So, you know that the heat flow rate Q through multi layers, okay, so can be expressed in the form of like this one. So just like with respect to one layer, U1, A1 is equal to delta T. Another layer, U2, A2 is equal to delta T. Okay. So, where U is the overall heat transfer coefficient, it can be expressed like this one. U1, A1 is equal to U2, A2 is equal to 1 by total thermal resistances. So, you know that thermal resistance for any solid surface like heat conduction in a homogeneous body, temperature T1, temperature T2, suppose temperature T2, thickness L, area A, then you know that Fourier's law, Ka into T1 minus T2 by L. It means Q is equal to temperature difference T1 minus T2 by L by Ka. So this L by Ka is the thermal resistance of conduction. Similarly, convection 1 by Ha. So these are the thermal resistance of the convection mode. Okay. So we have to sum of all the thermal resistances. Then 1 by sigma thermal resistance shows the overall heat transfer coefficient with respect to with area. So we can see this formula U1 A1 with respect to one surface. If you can say UI AI also for inner surface, U2 U naught A naught with respect to outer surface also you can take. So overallly UIA is equal to 1 by sigma RT. This is the thermal resistances. Okay. U1 A1 you can see U1 is the overall heat transfer coefficient based upon inner surface. You can represent UI also. Similarly, U2 is the overall heat transfer coefficient based on the outer surface also. Okay. So these are the different formulas for the overall heat transfer coefficient. U is equal to 1 by H naught plus L by K plus 1 by HA. So this is for plane wall. So suppose here I am giving the plane wall. This is the homogeneous body. This is the plane wall. So heat is transferred from hot fluid to just like cold fluid. So this temperature is equal to suppose T naught. This is the TA, temperature T1, temperature T2. Okay. So heat transfer coefficient of hot fluid, that is the just like H naught. Otherwise, you can see this is the inlet Ti. This is the temperature T8, HA or heat transfer coefficient HA. This one is the temperature T naught. Overall heat transfer coefficient to H naught. Okay. So in this case, so thermal conductivity K and the length thickness is equal to L. So in this case, the overall heat transfer coefficient U is equal to 1 by sigma R. Sigma R. So it means here if you take UIAI, right? UIAI is equal to 1 by you can see. So first one 1 by HA. So this is the convection process, HA, okay, plus L1 by K1 or L by K. There is one body, one plane, L by K. This is the thermal resistance of this body with respect to conduction. Next to convection process, that is 1 by H naught. Okay. So this is the formula. So 1 by H naught plus L by K plus 1 by H. So this is the overall heat transfer coefficient formula for the plane wall. For the cylinders, you can see overall heat transfer coefficient U naught is equal to 1 by H naught plus R naught by K ln R naught by Ri plus ln R naught by Ri into 1 by H. So you have to remember these formulas. This is the overall heat transfer coefficient with respect to inner surface. This is the overall heat transfer coefficient with respect to outer surface. Outer surface means first of all we'll see 1 by HA. Okay. So L1 by K into ln R naught by Ri plus Ri by R naught into 1 by HA. Okay. So these are the formulas you can refer to solve the different numericals which are based on the overall heat transfer coefficient. Okay. We'll see. Next one, we'll see fouling factor. What is fouling factor? So generally, the surface of heat exchangers do not remain clean because when the fluid is flowing on that surface, the chemical reaction will take place between the fluid impurities to surface of that tubes. Okay. Surface of the heat exchangers do not remain clean after it has been used of sometimes because the surface becomes foul with scaling or and deposits which are formed due to impurities in the fluid. So because the chemical reaction takes place between the fluid and material because of that some impurities which are in fluid, those impurities chemically reacted with the surface material, then automatically some scaling or some deposits, some sludges are formed on the surfaces. So because of that one, automatically heat thermal resistance uh, will be increased because the conductivity of that material will be decreased. So we have to address those problems. We have to consider those resistances which occurs due to fouling factor, fouling problem. So effect of these deposits affecting the value of overall heat transfer coefficient. Okay? Because overall heat transfer coefficient is nothing but 1 by sigma r. Thermal resistance will be influenced automatically. Overall resistance, overall heat transfer coefficient also will be influenced. Okay. So the effect is taken by introducing or adding the additional thermal resistances. So that is called fouling resistance. So you have to add the fouling resistance, so which occurs due to fouling factor. Then the formula will be like this one: 1 by U overall heat transfer coefficient with respect to foul. 1 by U foul is equal to RF fouling factor, resistance of the fouling, plus 1 by U clean. Okay. So for the U clean, you have to add the thermal resistance uh, to that surface also. RF. So RF is nothing but fouling resistance. Okay. So including fouling resistance, the overall heat transfer coefficient formulas has been given here. Have been given here. So this is the U naught. U naught overall heat transfer coefficient with respect to outer surface. This one is the overall heat transfer coefficient with respect to inner surface. So 1 by, so with respect to outer surface means you have to take first to outer surface conduction thermal resistance 1 by H naught. 1 by H naught. Next to fouling factor thermal resistance 1 R F naught. We have to, with respect to outer surface, first you have to add this one. Then R naught by K ln R naught by Ra plus R naught by Ra into thermal resistance of the fouling factor with respect to inner surface. Then thermal resistance of the inner surface. You have to add this. So you have to remember this formula. Similarly, overall heat transfer coefficient with respect to inner surface is equal to 1 by, here first of all, thermal resistance, convection resistance, that is the 1 by Hi. Then R effect, it means fouling factor, thermal resistance of the fouling factor with respect to inner surface, plus Ri by K ln R naught by Ri. Okay, R naught by Ri, Ri by R naught into Rf naught. So then thermal resistance of fouling factor with respect to outer surface. This one is the thermal resistance of convection process. So these are the formulas which are including fouling factors. So formulas of overall heat transfer coefficient with respect to outer surface, overall heat transfer coefficient with respect to inner surface. So by using these formulas, we will solve one numerical. Okay. The first one we will see. So water heated to 80 degrees Celsius flow through a 2.54 centimeter inner diameter and 2.88 centimeter outer diameter. The K is the thermal conductivity. The tube is exposed to an environment, so which is known to provide an average convection coefficient. So H naught, this is H naught. Outer surface overall heat transfer coefficient that has been given. So 3800 watt per meter square Kelvin. On the outside of the, okay, water velocity also given. Velocity of the water is equal to 50 centimeter per second. Here we have to calculate the overall heat transfer coefficient based on the outer area of the pipe. So this is the H naught due to the outer surface heat transfer coefficient that has been given. So we have to find out U naught, overall heat transfer coefficient with respect to outer surface. Okay. So you know that temperatures, water heated to 80 degrees Celsius and one more temperature. So that is the, so okay, 80 degrees temperature, water temperature has been given. So based upon this temperature, we can take the properties. So properties of the water. Okay. So properties of the water at bulk temperature, okay, 80 degree Celsius. You can take the properties from the data book. Here, density rho is equal to 974 kg per meter cube. This is the new kinematic viscosity is equal to 0.364 into 10 to the power minus 6 meter square per second. Thermal conductivity also given. This one is the Prandtl value. So these four properties of the fluid are very important to solve the rate of heat transfer of inner surface, because outer surface has been given. You have to find out the HA. If you know the H and H naught, you can find out the U naught. Okay. So here velocity has been given, means you can understand this is the forced convection process. So for the forced convection process, you have to find out the Reynolds number first. Here it is flowing through a pipe. So you can take the formula, instead of length, you can take the diameter. So Re is equal to ud by nu. Velocity has been given, diameter also given, 2.54 centimeters, means 0.254 meters, 0.0254 meters. Velocity, that is the 0.5, that one given already in numerical. 50 centimeter per second converted to meters, 0.5. so this one is the 0.254 meters. 0.025 per meters. So here 50 means 0.5. Next to kinematic viscosity, mu value is equal to already given, taken from the data book, that is the 0.364 into 10 to the power of minus 6. So if you solve this one, you will get this one 34890. Okay, so this is greater than the 3200. Okay, so we can understand this is the turbulent flow. By using this Reynolds number and turbulent flow, you can take the formula, you can choose this formula based upon the data book also. Okay, so this Nusselt formula with respect to T is equal to 0.023 RE to the power of 4 by 5 Prandtl to the power of 0.4. Okay. You know that Reynolds value, you know that Prandtl number value. If you substitute those values, you can find out the Nusselt value. So 135.7. Okay. If you know this Nusselt value, then you can find out the heat transfer coefficient related to inner pipe. So HL by K, this is the formula. Here we will take HI by HI L by K. Okay. Then you can find out the HI. So L here, L is nothing but diameter D, HD by K. So HI is equal to Nusselt value with respect to D into thermal conductivity by diameter. Okay. So this is the formula. If you substitute those values, then you can find out the HI. Then you have to find out the overall heat transfer coefficient. That is the formula is equal to like this one. Okay. So NR, that is related to overall heat transfer coefficient with respect to outer surface. So 1 by H naught. H naught has been given. Then R naught by K into ln R naught by Ri plus R naught by Ri into 1 by H. So 1 by H already we solved that one. 3575. H naught already given in numerical. You can take that one. Okay. So if you substitute all these values in this formula, then we will get overall heat transfer coefficient with respect to R naught. So that is nothing but 806.9 watts per meter square Kelvin. So this one, in this way, just we can solve the overall heat transfer coefficient with respect to U naught, outer surface, overall heat transfer coefficient with respect to inner surface, we can find out. Okay. If the one pipe is given, we can take like this one. If the more pipes are given, we can so add the remaining radiuses also. Okay. So this one, so in this way, we can solve the numericals. This one is the fouling factor. So surface of the heat exchangers do not remain clean because already I explained this one. So these are the formulas. Okay. So one more numerical you can see here. Determine the overall heat transfer coefficient U naught. You have to find out overall heat transfer coefficient with respect to outer surface based on the outer surface. The diameter, outer diameter also given 2.254 centimeter. Inner diameter is equal to 2.286 centimeter. Heat exchange tube, thermal conductivity also given. The heat transfer coefficient at inside and outside. So HI also given, H naught also given. Both the heat transfer coefficient with respect to inner surface and outer surface. So both are given. Then fouling factors also given. F R naught, R F naught, R F y. Both are same. Then you have to find out the overall heat transfer coefficient. So you know the formula U naught is equal to 1 by H naught, R F naught, R naught by K into ln R naught by Ra plus R naught by Ra into F R F y. Next to R naught by Ra into 1 by H. Okay. So if you substitute all the values, here, then you can find the uh, overall heat transfer coefficient with respect to outer surface. Similar way, you can find out the overall heat transfer coefficient with respect to inner surface also. The formula will be changed 1 by Hi Rfi Ri by K into ln Ri by R naught, Ri by R naught into R F naught. Okay, Ri by R naught into 1 by H naught. So this is the formula. So in this way, you can find out the overall heat transfer coefficient with respect to inner surface also. So this is the value overall heat transfer coefficient for with respect to outer surface. Okay. So these are the different test books you can prefer to solve the different numericals. Thank you listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.